We are in section 6.6, topics from number theory. The first thing that we're going to talk about here is what is a proper factor, and then we're going to use the idea of proper factors to determine if a number is perfect, deficient, or abundant. A proper factor is a factor of a natural number that is not the number itself. For example, if we have 6, the factors we found in the previous lesson were 1, 2, and 6. So its proper factors will be 1, 2, and 3. We're not going to include 6. Now let's figure out what they are for 20. When we look for the proper factors for 20, we know we have 1 and 20, 2 and 10. 3 won't work because 2 plus 0 is 2, and that's not divisible by 3. 4 and 5, and then 4 and 5 are next to each other, so we know we got them all. So then our proper factors, so our factors would be 1, 2, 4, 5, 10, and 20. But the proper factors are going to be 1, 2, 4, 5, and 10. So again, we're not including the number itself. So now if we want to determine if a number is perfect, deficient, or abundant, we're going to take the sum. And then we compare it to the actual number. So now we're going to take the sum of the proper factors. And again, we're using the proper factors here, not the regular factors. So this would be 1 plus 2 plus 4 plus 5 plus 10. When we add those together, we get 22. And then we compare 22 versus 20. Well, 22 is bigger, so this is called an abundant number. So when the sum is bigger, it's abundant. When the sum is less, like we see in the next example, 6.6.1c, it's deficient, and when they're equal, it's a perfect number. So 20 is abundant. Another way to determine a number type is 2 to the n minus 1. So these are called Mersenne numbers. So Mersenne was a French monk interested in prime numbers. So some are prime, some are composite. So what we're going to do is we're going to look at 2 to the 5th minus 1 in example 6.6.2, and we're going to determine if this Mersenne number is prime or composite. So 2 to the 5th would be 2 times 2 times 2 times 2 times 2 times 2. 5 2's multiplied together, minus 1. So I'm just going to do this out longhand just to make sure that we understand how this works. So we get 4, 3 2's are left. Then we get 8, 2 2's are left. 16, 1 2 is left. So we get 32 minus 1. Now 32 minus 1 is 31. The square root of 31 is going to fall between 6 and 5, because 5 squared is 25 and 6 squared is 36. So we know it's going to be between 5 and 6. So we only have to check the numbers up to 5. So we know we're going to have 1 and 31. 2 won't work because it's not even. 3 won't work because 3 plus 1 is 4, and that's not divisible by 3. 4 won't work because it's not even. And 5 won't work because it does not end in a 5 or 0. So that means that our only factors will be 1 and 31. So 31 is prime. But again, here we want it as the Mersenne number, so that means 2 to the 5th minus 1 is prime. So Euclid used the Mersenne numbers to figure out if it's a prime number. So for this to work, n and 2 to the n minus 1 both have to be prime, and then we can generate the perfect number by 2 to the power of n minus 1 times 2 to the n minus 1. So we've already done this for n equals 3, so you can read that on your own in the professor's notebook. We're going to go ahead and do it for n equals 5, and then the homework you do it for n equals 7. So here we have n equals 5. So first we're going to find the value of 2 to the n minus 1, where this is in the exponent. So we get 2 to the 5 minus 1. So 2 to the 4th, which would be 16. Then we're going to do 2 to the n minus 1. So 2 to the 5th minus 1. Well, we just did that one. We said it was 31. So then the perfect number should be 2 to the n minus 1 times 2 to the n minus 1. So 2 to the 4th times 2 to the 5th minus 1, or 16 times 31, which in our case gives us the value of 496. You prove that this one is perfect in the homework, so we're not going to do that here.